Hey, we're back. We're going to begin lesson 3.2 today. You can see that it's going to go over a couple of days. Our lesson is about logarithmic functions, and today the focus is pretty much on properties of logarithms and remembering that exponentials and logarithmic functions are inverses of each other. You'll recall when we talked about inverses before that you switch x and y and solve for the new y. I'd like us to see how that plays out in this particular case. We start with the exponential function y equals b to the x. In logarithmic terms, that becomes x is equal b to the y, and to write this in log form, we would say y equals the log base b of x, or y is the power you raise b to, the power you raise b to, in order to get x. One of the teachers, y is the power you raise b to in order to get x. So y is the power you raise b to get x. That's the definition, if you will, of the logarithmic function. One of the teachers that used to work here very often had his students repeat and repeat and repeat. Y is the exponent. Y is the exponent. It's the power that you raise b to. Y is the exponent. He really wanted them to understand that the logarithmic function defined this way, y equals log base b of x, which is exactly what we have above, where both, by the way, b is greater than 0, x is greater than 0, and b not equal to 1. It has to be bigger than 0, but it can't be 1, otherwise that would be crazy, because 1 to any power is just 1. So in general, folks, y equals log base b of x is equivalent to b raised to the yth power equals x. That's something good to remember, because this is how we translate from one form to the other. Let's take a look at writing some of these equations in their equivalent exponential form. The base of this problem that says 3 equals log base 7 of x, the way that you would write that, 7, remember y is the exponent, 7 raised to the third power would get you x. Again, that's just applying that whole definition of the logarithmic function. Try it here. This one would say, well, the base of the exponential expression is 2, the exponent is n, 2 to the n equals 25. Here's one for you to try. This one uses the natural logarithm, whose base is e. If we're going to write this in equivalent exponential form, we would say e raised to the yth power equals 26. Okay? All right. Here we go in the other direction. Write each of these exponential equations in their equivalent logarithmic form. Well, the base, so we'd say log, the base here is 2, log base b of x equals 5. That is, 5 is the exponent, or the power you raise 2 to get x. Try that here. I know that you're remembering this from before, but you'd say log base b, this time, of 27 equals 3. The exponent is the logarithm. The exponent is the logarithm. How about here, where our base is e? So we're going to be talking not log, but ln, okay, natural log. So let's see, that would work out. The natural log that assumes base e of 33 equals y. Y is the exponent that you raise e to get 33. It takes just a little bit of practice to go back and forth between those formats. Let's see if we can evaluate these logarithms, and I'll show you the way I think of this. Not everyone does it the same way. I like to put a variable in here, because then I can apply what I did up here. 10 to the xth power equals 100. Well, to get 10, what power do you raise 10 to get 100? x has to be 2 here, or you raise 10 to the second power to get 100. Again, I like to introduce the variable there and say 5 raised to what power gets me 1 to the 25th? Well, I remember a little bit about these things. Where we've got a fraction here, then we're really talking about negative exponents, and it takes negative 2 powers of 5 to get 1/25. Try that here. How many powers of 36 does it take to get 6? Well, 6 is the square root, or the 1/2th power of 36. So x would be 1/2 there. That introducing the variable helps me. It may or may not help you. Many people can see this without introducing the variable. They would just say, yeah, to get 1/25, I need 5 to the negative second power, since that's 2 powers of 5 underneath a fraction, or in the denominator of a fraction. I know the variable helps me to work my way through that problem. As we go on, we want to talk just real quickly about some basic logarithmic properties. We're going to investigate logarithms a lot more closely in the next couple of days, but some of these things are properties that just make sense. If this thing says, what power do I raise b to in order to get b? You guys, that has to be 1, because b to the first is equal to b. Again, that's just a common sense property here. This one, what power do I raise b to in order to get 1? You guys, that has to be 0, because anything to the 0th power other than 0 is 1. So some properties involving 1. The power, or log base 9 of 9, the power I raised 9 to get 9, y'all, that's 1. And the power I raise 8 to in order to get 1, well, that's just got to be 0, and that's just applying those two. Now we want to talk just a little bit about the inverse properties of logarithms, remembering that b has to be bigger than 0 and not equal to 1. In these inverse properties, again, this is going to seem sort of like common sense to you. This first one, if we were reading this, it would say the power that you raise b to get b to the x, that's got to be x, folks, because b to the x is what is equal to b to the x. That's just common sense. As we take a look at the second of the inverse properties, it looks kind of weird. If you were reading this, it would say b raised to the, well, then the exponent here is the power that you raise b to get x. b raised to the power that you raise b to get x, well, that exponent has to be x, because log base b of x is the log base b of x. Okay, that just kind of makes sense. Again, it's kind of convoluted. b raised to the power that you raise b to get x is x. All right, I can go with that. Let's see if we can apply those kind of strange inverse properties here. This one says 7, what power do I raise 7 to in order to get 7 to the 8th? Well, that power would be 8. The logarithm is the exponent. This one says 6 raised to the power that I raise 6 to get 9 is equal to 9. If I raise 6 to the power that I need to raise 6 to 9, I should get 9. That's the inverse properties, folks, and they're a little bit odd. So we have just come to the end of today's mini lesson. Tomorrow we'll investigate these properties in class. Right now, I need you to try the U-try. So y'all have a good evening. Bye-bye.